applied. So here we're talking only about applied loads, applied forces. Please ignore the constraint forces. All applied forces vanishes. This work vanishes. So W summation each force, I'm dotted with dr I. This is 0. This is the principle of virtual work. This is not all the forces, these are the applied only. So please ignore the constraint forces, they are unknowns. Just live without them happily. And this equation is at equilibrium only, there is no motion. So if all the forces should cancel each other at equilibrium, if all the forces should cancel each other at equilibrium, so summation of all the forces is 0. If you dot it with R, you get a similar equation to this. But then the constraint forces don't produce any work, so just ignore them. So you live with this equation. Let's have some example. Any questions so far? Any question, please? Like I said, this is new stuff, and we would be more than glad to discuss. You enrich your colleagues, and you teach me new stuff. So feel free to come up with any funky idea or question, whatever. So this is an example in 6.1 in what book is that? This is Greenwood. Example 6.1 in Greenwood. Giving you two masses. Okay. So this is 1, 2. There is an applied force here F at some angle theta. He is asking what is the required force F to produce equilibrium at this particular angle theta. That's it, this is the question. Simple question. There's no dynamics in there. We just want to see how to apply this. I mean, again, this is an easy example. So solving it using Newtonian mechanics and analytical mechanics, it might not be that different. But we just introduced it here to see how to apply this guy. Okay. Still, you will see the difference between Newtonian mechanics and analytical mechanics. So let's do it. I wish I do it here, but anyway, let's do it using Newtonian mechanics. Okay? How are you going to do it using Newtonian mechanics? I have to draw a free body diagram. So this is the first mass, right? The first mass, I have what loads applied on the first mass? I have M1G, right? What else? What else?
The normal.
The normal force, so I have N1. What else?
Linkage.
Exactly, this rigid interconnection, I have some tension or whatever, right? And here is your theta. And how many equations will I write for this mass? Two, right? Horizontal and vertical. The horizontal one says N1 minus T sine theta. This should equals mass times the acceleration in the x direction, but it's 0 because we are at equilibrium. The second equation says that T cosine theta minus M1G is again 0 because there is no motion along the y. Any question about that? Still not done yet, because here how many equations and how many unknowns? There are obviously two equations, how many unknowns?
3.
3, which are
N T theta.
N1,
T and theta.
T.
And theta.
No, they are, I mean, theta is given.
Theta is given?
Yeah. So two equations into unknowns, you solve them and get T and N1, but this is not what is required. This requires the force F. Okay, so we're gonna do it anyway. Let's see here. Here is this guy. We have T, right? We have M2G, we have N2, I have theta, and I have your force F. You're gonna write similar two equations. What are these two equations in the x direction? In the x direction, what do we have? We have
F.
T sine theta minus F equals 0, and we have N2 minus T cosine theta minus M2G equals 0, right? So, if you need the force, please get T from here, substitute it there to get the force as what? Force equals M1G divided by cosine times sine, so this is tan theta. This is the solution of the problem, correct? Okay? Let's do it using our principle of virtual order. So this is our problem. How many degrees of freedom with this?
One.
One, right? Which is, I mean, you are free to take whatever you like. Let's take theta, okay? So this is the x of this guy, this is the y of that guy. So my q is simply theta. In terms of this theta, actually x is what? Whatever. Let's get the position vector of each mass. So R1 is what? What's R1? R1 is simply y in the j direction, and this y is L cosine theta. Okay? So this is L cosine theta in the j direction. R2 is x in the I direction, which is L sine theta in the I direction. Okay? You get your positions, simply differentiate to get the virtual displacement. We didn't talk about that, we need to talk about it now. Let's differentiate this guy, please. So this is negative L sine theta d theta, right? This guy is L cosine theta d theta in the I. Any question about that? Any question, please? I'll give you some time to write, but just bear with me for a minute. So all what I need now is the acting forces here and acting forces there, and I'm done. What's the acting forces on the mass 1? Well, I already did it for Newtonian mechanics, but actually I'm going to ignore a bunch of them. What is the acting force on this mass?
mg.
Simply mg. All the other things, they're just there to induce constraints, and I'm happy with the constraints, and I'm also happy with ignoring them. So this is negative m1g in the j direction. What about the second mass?
F.
F, because this is applied, and you have m2g, right? So F in the I direction minus m2g in the j direction. Simply do dot product for these two guys. So this is actually T work. It's as simple as this. Dot product, so the similar components multiplied each other. So JJ here, so this is M1G L sine theta d theta. And from here, I with I and J with 0, so it goes away. This is F L cosine theta d theta. and this is 0 because of the principle of virtual work. This is the equation. This is our meat. And this is 0 for any d theta. For any d theta. So in particular, this guy is 0, giving you directly your force, which is m1g tan theta. Okay? So this is how do we apply the principle of virtual work. Just one thing that we did not discuss, actually. Any question for moving in? Any question, please? Please don't pass things.
Didn't you say that for the postulate that constant forces are worthless?
Worthless. So this is why I ignored all the constraint forces. Or the constraint.
Oh, constraint, right?
Yes.
Okay.
So last time,
Why are you using D instead of dot? Like DW instead of W dot?
Okay, I'm going to discuss it now in a minute. Yeah, thank you. You have the same thing? Any question, guys, about the problem? We're discussing this. I should have discussed it at the beginning. This is called the virtual work. It's not the work. What's the virtual work? Well, simply the work is force times displacement. So this virtual work is force times virtual displacement. Virtual displacement. So it's the work by forces through